For decades, cosmologists have navigated space and time using a single, highly reliable mathematical map. But right now, the most exact measurements in human history are actively tearing that map apart. This map is the standard model of cosmology, known as Lambda CDM. It has functioned as an unimpeachable cosmic ledger, predicting the behavior of the universe with staggering accuracy for half a century. The model balances on three core ingredients: Einstein's general relativity governing gravity, invisible dark matter holding galaxies together, and a fixed cosmological constant, often called dark energy, driving the expansion of space. If this proven ledger is wrong, our base understanding of reality is broken. We wouldn't just need to adjust a few numbers, we would need an entirely new framework of physics. The catalyst for this crisis is the deployment of ultra-advanced observational tools. Instruments like the James Webb Space Telescope are capturing light from the furthest reaches of space with an exactness we have never had before. Rather than confirming our established theories, this highly sensitive equipment is returning data that contradicts them. Cosmologists are currently trying to reconcile three distinct, massive anomalies: the rate at which space is expanding, the way matter clusters together, and the actual chemical makeup of the earliest stars. To see how deep this failure goes, we must audit the cosmic ledger and look at the specific data driving each of these discrepancies. The first crack in the model is the Hubble tension, which concerns the physical expansion rate of the universe. This graph illustrates the discrepancy. The lower line shows the expansion rate predicted by measuring the cosmic microwave background in the early universe, about 67 kilometers per second per megaparsec. But the upper line shows what we actually observe in the late universe by measuring nearby stars. They show space expanding at 73. In physics, a 5 sigma result is the standard requirement for a definitive scientific discovery. This gap represents a 7 sigma tension. It is mathematically impossible for this divergence to be a rounding error. Repeated observations have consistently confirmed that these local measurements are accurate, ruling out faulty equipment or human error. The data is definitive. The universe is currently expanding faster than our established laws of physics allow. The second anomaly is the S8 tension. This is a metric that quantifies exactly how tightly matter is clumped or clustered together across the cosmos. When cosmologists run the baseline data from the early cosmic microwave background forward, the standard model projects a universe where matter is highly clustered and dense. Yet massive late universe surveys utilizing weak gravitational lensing, like KIDS and the Dark Energy Survey, measure something different. They show a late universe that is significantly smoother and more spread out than the math predicted. This structural mismatch implies that gravity, or the matter it acts upon, is behaving differently over cosmic time than Lambda CDM dictates. The third anomaly, the primordial lithium problem, forces us to look back at the actual elemental composition forged in the first few minutes of the universe. The foundational math predicting the Big Bang's creation of elements was developed by a historically overlooked physicist named Ralph Alpher. Alpher's nucleosynthesis equations perfectly calculate the amounts of hydrogen and helium we see today. But those same equations predict 3 to 4 times more lithium-7 than we actually observe in the oldest metal-poor stars. For decades, physicists assumed the missing lithium was hidden deep inside stellar cores, but modern high-resolution spectroscopy confirms the discrepancy is real. This leaves cosmologists cornered. The model fails on expansion, fails on matter clustering, and fails on chemical composition. The ledger is unbalanced. The search for a solution leads to the DESI collaboration, which recently completed an intricate 3D map tracing 11 billion years of cosmic history. This chart maps a shocking finding from DESI. Dark energy has long been assumed to be an unchanging cosmological constant, represented by this flat line. But the newest data shows strong statistical hints that dark energy is actually weakening, curving downwards as the universe ages. If dark energy is time-varying, it alters the historical growth rate of cosmic perturbations and expansion. By factoring in this evolution, the previously misaligned data points from the Hubble and S8 tensions suddenly snap into alignment. If dark energy is unstable, the trajectory of the entire universe changes, forcing a complete recalculation of how and when the cosmos will end. Breaking the cosmological constant opens the door to radical new theories of reality, such as theoretical physicist Roger Penrose's conformal cyclic cosmology. This hypothesis argues the universe has no single beginning. It posits an infinite series of cycles, where the infinitely expanded, freezing future of one universe mathematically transitions into the hot, dense Big Bang of the next. These terrifying discrepancies in our data are exactly what astrophysics needs to move forward. These specific failures in the data provide the transition point for a total revision of cosmology. The Standard Model has hit its limit. We are now looking for the physics beyond it.